The Planck length is the smallest known length where if we went beyond it the laws of physics as we know it breaks down completely. That doesn't mean that it is the smallest length in the universe. It is just that we are ignorant about what happens after that particular length. Possible solutions to this problem are that we might need a quantum theory of gravity which can be derived by unifying relativity with quantum mechanics. Or, replace modern physics with something else. Possibly a new form of physics if we wish to what happens after this length or even if it is really the smallest length in the universe. The Planck length was initially derived with the basic consideration of gravity and quantum mechanics. Speaking of quantum mechanics, let's begin with the Heisenberg uncertainty principle states that a particle cannot simultaneously have a precise position and momentum. In other words, the uncertainty in a particle's position times the uncertainty in its momentum must be greater than h bar, which stands for the Planck's constant. Now, we must point out that there must be some uncertainties, or else the Heisenberg uncertainty principle will be violated. In depth, if one claimed the precise position of a particle in any given region in space, the uncertainty change in position will be 0 times the uncertainty change in momentum is 0. Now, the equation states that nothing on the left side is greater than h bar, meaning that no uncertainty exists, which explains the violation. Thus there must be some uncertainty despite how pesky it may appear. Furthermore, let us imagine a region of space with a radius of L if we wish to know the uncertainty change in the position of a particle in that region. We would have an equation expressing that the uncertainty change in position is less than L, but if the expression was larger than L, then that means that the particle could be found outside the specified region. But since we only wish to find it in the specified region, we would express it to be less than L. The next step is to substitute this expression into the Heisenberg uncertainty principle to get a relation between L and the uncertainty change in momentum. After some algebra, we derive this expression, which states that very small scales require high momentum. But why? To understand this, let's blog this expression into special relativity. And now, this tells us that very small scales require high energies, which resonates with the relation that of L and momentum, since high momentum requires high energy. Remarkably, this illustrates why the largest particle accelerators, in order to produce particles such as quarks, neutrinos, and Higgs, extremely high energy is needed. Moreover, this expression for energy can also be written in terms of mass, since according to Einstein's most famous equation E equals mc squared. Mass can be converted into energy, and energy can be converted into mass. In other words, mass and energy talk to each other respectively. This means that this energy expression behaves like a gravitating mass. Let's illustrate this in a demo. Let's take two electrons and separate them by distance r. We know that the electrons have negative charges, and since like charges repel, we would expect them to be repelled. But according to Newton's law of gravitation, any two masses close to each other should attract. Similarly, the two electrons contain mass and thus will attract. But not so fast. What has been said so far about the electrons drove the conclusion that they should be repelled and attracted at the same time. Well, from an experimental point of view, and our current modern understanding of the fundamental forces that govern our universe, implies that the electromagnetic force is far stronger than the gravitational force. In fact, the electromagnetic force is 10 to the 36th power stronger than gravity. And that explains why magnets with the same poles are seen to repel more than to attract. Back to our energy expression, as these electrons come closer and closer together, the energy or mass of the electrons will increase significantly, such that the gravitational attraction between them will also increase significantly. This process can go on until the ratio between the electromagnetic force and that of gravity equals 1. What happens next to the gravitational force as the distance between the electrons gets even closer? You guessed it, it will increase, resulting in a ratio greater than 1. But note that this process with any masses will not be allowed to proceed forever due to the phenomenon of the Planck length if it ever reached it. Ultimately, the Schwarzschild radius states that if a mass was to be shrunk into a specific radius, then it must collapse to become a black hole, meaning that as the electrons get closer and closer together, their mass and energy will turn so greatly that they can possibly be turned into a black hole. To form a black hole, the electrons will have to be squeezed to a radius of 10 to the 34th power meters. But regardless of what has been said, there is a misconception debate between physicists and cosmologists today regarding the smallest possible mass, such that, if squeezed to its Schwarzschild radius, will turn it into a black hole. And we believe that this is the Planck mass. The underlying notion here is that as long as the Schwarzschild radius of a given mass does not exceed the Planck length, then it is considered to be valid, else it will disturb and confuse us since the physics beyond this scale is not well known. But could a mass smaller than the Planck mass exist? That's a question that is worth waiting for. Thank you for watching this video. Please subscribe and share this video for future content. Until now, see you next time.